There you go. All right, so it's a pleasure today to have Alessio Lerose with us, who is from University of Geneva at the moment. And he will tell us about the influence matrix approach to quantum many-body dynamics, which is something they've been working on quite a lot recently. So we're looking forward to it. Please go ahead.
Thank you. Thank you, Zlatko and Achilles, for the invitation. I'm happy to give this seminar, and of course I hope to have a chance to meet you in person sometime in the future. Okay. So yeah, as Zlatko anticipated, I'm going to present some recent work, an approach, specifically an approach to quantum many-body dynamics that we've been recently developing in collaboration with Michael Sonner and Dimitri Abanin at the University of Geneva. And this is based on these papers that you see at the bottom of the slide. And I mean, there's also some, as you will see, there are many still unexplored and some questions still to be answered. So it's really an open-ended presentation, and any input from your side is of course most welcome. So please don't hesitate to interrupt me and to interact and ask questions, and you're most welcome. Okay, so let's go. Let's see. Okay, so essentially in one line, the problem that we want to address is we want to characterize the influence of our quantum many-body systems, out of equilibrium, on the dynamics of its local parts. Okay, so just to make the introduction more concrete, let me just consider a simple quantum many-body system, so such a spin chain, where each spin in the spin chain is just prepared in a simple state, completely uncorrelated. For example, as you see in the slide, this fully polarized spin state. And then we consider its evolution, unitary evolution generated by a Hamiltonian that involves interaction between the spins. Now, during this evolution, the spin will accumulate correlations, so entanglement will develop between remote degrees of freedom. But the evolution of the global system is coherent, meaning it's fully unitary. But now what we are typically interested in is looking at a local region, so a finite part of the system, zooming on that, and looking at quantities that we can access in this region. And when we do so, the evolution of the observable, so the evolution of the system in this reduced part will not look coherent, will in generally look perhaps noisy or dissipative. Okay, so what we aim for is essentially to describe in this dynamics of the reduced system. And now there are two sort of extreme paradigms in this kind of problem, which is on the one side, the generic behavior that you would expect is that of thermalizing systems. So thermalizing system, the way you normally phrase this, is that the system is the ability of the system to act as a thermal bath for its own subsystems. So essentially, the system locally approaches thermal state due to the action of the rest of the system. On the other hand, not all systems are able to do so. So in particular, there is one class of system, that of many-body localized systems, that is not able to do so and retains, on the contrary, retains memory of the initial condition locally, essentially forever. Okay, so the way you say this is the system is a bad bath, meaning it's not able to provide a thermal bath for itself. Okay, so this is the dichotomy. And how do you describe this? Well, there are in last, say, I would say last decades, many theoretical approaches have been introduced to study this, and so there are many of them. So, for example, one very common probe is that of spectrum, so the spectral diagnostics, and this is used to probe things like matrix elements of local operators between many-body eigenstates, and probing for example, the emergence of random matrix theory universality of level spacing and things like that. This is of course limited by system size because of the exponential blow up of the Hilbert space of the many-body system. On the other hand, you can study time evolution of larger system with approximate methods such as tensor network algorithms. And this is sort of complementary because it's limited by another quantity, which is the growth of entanglement entropy, which typically accompanies the process of thermalization. And most recently, people have started studying this problem by looking for exactly solvable models, where, of course, here the price you pay is that you have to generally fine-tune your parameters, but on the other hand, you can get some insights into the problem. And this is, I'm thinking especially about these solvable, well, some unitary circuits, where a novel kind of solvability, a novel notion of solvability has been proposed, such as random unitary circuits or random Floquet circuits with large local Hilbert space or dual unitary circuits. Now, essentially, what we want to do is something complementary to this approach, to these approaches. In particular, we want to take this suggestive punchline of good buffs, good thermal buffs versus bad buffs, and turn it into a formal tool to study quantum many-body dynamics, and in particular, thermalization and the failure of thermalization. So this is the general goal. And the way we do this is inspired by an old idea, well, as many other interesting ideas in theoretical physics. This goes back to Feynman. In particular, back in 1963, Feynman and his PhD student Vernon proposed an idea to study the effect of quantum buffs. Okay, so of a general system coupled to quantum system coupled to some buff. Okay, and the way, well, this approach actually has been probably made most famous by Leggett and co-workers, which in subsequent years used it to apply it to studying the dynamics of a simple system, say a two-level system, coupled to some environment composed of harmonic oscillators. That's the simplest way you can model an environment. And in this, well, and also most recently, it has been applied to other problems such as transporting nano devices. But yeah, so this approach is has been called by Feynman the influence functional approach. And the way it goes is the following. So essentially, imagine we take this Leggett problem, so a two-level system coupled to some buff, okay? And we are interested only in the dynamics of observables that pertain only to the system and not to the environment. So the environment is thought of something that we cannot really control. So we are interested in the dynamics of things happening in the system. And the way you can express this is you can express via path integral. Okay, so something that Feynman introduced actually. So in this case, a Keldysh path integral, meaning we have two families of trajectories that we conventionally call forward and backward in time. And we express our dynamical observables as a summation over these trajectories, okay? And in particular, one way of expressing this is to express it as a summation over trajectories of the system only. And we encapsulate all the weight arising from the trajectories of the environment into a functional that we call this I of sigma bar. So sigma and sigma bar are this forward and backward in time trajectory of the system. And this functional is nothing but what Feynman called the influence functional. And it arises from integrating out the trajectories of the environment. Okay. All right. So essentially some intuition for this function. Well, this functional knows everything about the environment. So it's a defining property of the environment dynamics and initial state. And well, one way to think about this to get some rough intuition is if you think that your system is linearly coupled to your environment. So imagine this S-int, this interaction term is a linear coupling. Well, you realize that this is a sort of a Fourier transform of the action describing the dynamics of the buff. So in this sense, this guy is essentially a generating functional of the quantum noise produced by the environment. So it incorporates all dynamical information of the environment relevant to the dynamics of the system. Okay, so this is the general tool. And of course, you can this has been computed for this buff of harmonic oscillators, because in that way you can carry out the computation and get an explicit expression for this functional, which you can use to get some knowledge on the system dynamics, which is in general still quite complex, because, for example, unlike the system action, which is typically local in time, it's just the integrated Lagrangian of the system. This action instead is non-local in time, and this is due to, of course, to the delay due to the temporal correlations present in your buff. Okay, so we want to use this approach to study quantum many-body dynamics, where the distinction between system and environment. So we want to focus on a local region and call it the system, and the external part of the system, of this subsystem, we want to treat it as an environment for it. Okay, so here, unlike in this legged problem, here the degrees of freedom of the system and the degrees of freedom of the buff are actually the same thing. So there is no, the distinction is purely conceptual. There is no natural notion of system and environment. But still, we want to do that, and formally we can do that. So the way we do this is we take our, well, for simplicity, we take this spin chain that we introduced and focus on a local region. For example, focus on spin P at position P along the chain, and treat all the spins to the left of this spin as an environment for spin P. Okay. So what we do is we write the Keldysh path integral for this spin chain for its evolution from time 0 to some time t. Okay, and we integrate out all the trajectories of the environment, of what we call the environment, and in this way we end up with a functional of the trajectories of spin P. Okay, so an object that depends on the forward and backward trajectory of spin P. And this object is nothing but the influence functional of this quantum many-body system. And in general, it's a very complicated object, of course. But the crucial observation you can make in this particular setup is that this complex object here has to satisfy, well, at least for translational invariant systems, meaning translational invariant dynamics and initial state, this object has to satisfy a self-consistency equation. And the intuition for this is very simple. It's just the statement that if we have the influence functional acting on spin P due to the spins to the left, and we incorporate another spin, so spin P into the buff, this combined environment should produce exactly the same influence functional for the next spin at position P+1. This is quite easy to see, but as far-reaching consequences, because this will allow us to study, well, essentially to obtain this object in some respects. Okay, so this is phrased in very general terms, but now let me be more concrete and make it more concrete by considering a specific model, which is essentially the simplest model you can think of, but it's still expected to retain the full complexity of the generic case. So we consider this kicked Ising chain. So for simplicity, we make our model Floquet. So we make our model naturally discrete in time by considering periodic kicks acting on our spin chain. So our spins interact by a local nearest neighbor interaction of Ising type, and periodically in time they are kicked with some with some spin rotation, which is acting on a generic, say, around the generic axis. Okay, so there is generally no integrability in this problem. Okay, and now one way you can represent this Keldysh path integral that we spoke about before is to write your model as a quantum circuit, or which is the same as a tensor network. Okay, so you consider the density matrix of the spin chain, which we assume to be simple product state, completely uncorrelated, and essentially you can write the matrix elements of the gates acting on your spins as tensors or as unitary gates acting on. So there is this alternative view on the dynamics. Okay, and now to implement the general idea I introduced before, we want to focus on spin P, and we want to essentially sum over all trajectories of the environment. So we have a left environment and a right environment, and this summation over all trajectories in this language amounts to contracting this tensor network, or contracting this circuit in the space direction rather than time direction. Okay, so the result of this contraction is this big rectangle, this big pink object, which is a tensor whose legs are along the time direction rather than on the space direction. So it can be thought as a sort of state of a fictitious system, but developing in time rather than in space, sort of many body wave function in time. Okay, and we have one for the left environment, one for the right environment. And now you see that everything we need to know for understanding the evolution of a local region is incorporated in this big objects. And the self-consistency equation in this language takes a nice mathematical form, which is the statement that this object, this influence functional, this pink tensor, has to be an eigenvector, in particular the only non-trivial eigenvector, as you can prove, of a transfer matrix acting along the space direction. Okay, so it must be an eigenvector with respect to eigenvalue 1, and you can actually prove that this transfer matrix has a very trivial spectrum. It has only one non-trivial eigenvector, and the rest is actually nilpotent, so null Jordan blocks. So essentially, the spectrum of this transfer matrix contains no information at all. All the information is incorporated in the structure of the eigenvector, which has the physical meaning of Feynman-Vernon influence functional for this many-body system, of a self-consistent influence functional. Now, this procedure of contracting the tensor network in the space direction was actually known in the tensor network community. It goes back to this physical review letters paper by Mari-Carmen Banyuls and collaborators. But now, essentially, what we want to do is we want to link the structure of this object to the physics of the problem, so to the basic dynamical properties of the problem. Okay, so this is the practical implementation of the idea I discussed before. But now let me just pause a moment and say survey what we get and what we hope to get from this kind of approach, and then I can get to the technical details. So the first thing to notice, which is actually what we think is the most appealing feature of this approach, is the fact that this influence function knows everything about the evolution of the reduced density matrix of local systems. So in particular, it knows everything about the basic properties of essentially the dynamical phase, the universality class of the dynamics of the problem. For example, it has to incorporate the fact that the system is thermalizing or not. Okay, and in particular, it will be very interesting to link the properties of this many body wave function to the basic physical properties of the system. So, for example, it's what we call this temporal entanglement, which is the entanglement associated with this fictitious many body wave function. So you see, the sort of the hope of this approach is that the role played by the influence functional is akin to the role played by the ground state in equilibrium, meaning that it is the right object to classify universality classes of dynamical phases, as I just said. So this is where we want to go, essentially. And yeah, so as I will discuss soon, this approach gives you say a complementary principle of efficiency in the computation of quantum dynamics, and in particular, it opens a new corner of solvability, meaning there are problems that become solvable when attacked in this way, which wouldn't be solvable in conventional approaches. And in particular, this will be the class of perfect dephaser points, where the notion of solvability is related to the fact that the dynamics of reduced subsystems, of finite subsystems, turns out to be exactly Markovian. This, of course, is a very surprising property, but this happens by fine-tuning your model parameters. So I will discuss this. And again, the appealing feature of this, the interesting aspect of this is the fact that the notion of easiness essentially is related to the fact that the system is able to forget very rapidly. So is a very so-called strongly chaotic buff, which implies in turn that this object has very short range correlations. Okay, and in particular, it has low temporal entanglement, and therefore it can be efficiently represented, for example, as a matrix product state. Okay, this despite the fact that the system is developing spatial entanglement between remote degrees of freedom, but those are precisely the degrees of freedom we want to forget. Okay, so we are all interested in what happens locally, so this procedure automatically takes into account this thing. Okay, so in particular, what I will also discuss is how to link the structure of this of the influence function, of the influence matrix, as we call it, because of its natural discreteness in time for Floquet problems. How to link it to the physics, in particular, how to make predictions on thermalization of local subsystems, and how to make statements about this the scaling of temporal entanglement. And also, in the last part, I will try to describe what happens to this influence matrix when you go across an ergodicity breaking transition, in particular, transition to a many-body localized phase. Of course, this has to be incorporated in the influence matrix because that knows everything about the local dynamics. So, in particular, the feature of having persistent local memory must show up here, and I will discuss how to get advantage of this. Okay, so that's sort of the rough plan. Yeah, okay, so let's start from the first point I mentioned, so perfect dephasers. So perfect dephaser is essentially the simplest action of a quantum buff you can consider, which is just a buff that fully, at each time step, it fully dephases. Well, essentially it measures the spin, your subsystem, so your spin, it measures completely. So it measures, for example, the Z component. Okay, so that's the simplest action you can conceive. That might seem to be unrealistic to hope for many-body system that realizes this, but actually this turns out to be the case. Okay, so the surprise is that if you take your well, in particular, let's stick to this simple model that I introduced. This kick is in chain. If you tune the kick parameter and the interaction parameter to some special values, which is pi4 in this case, it turns out that this simplest form of the influence matrix, this perfect dephaser form, satisfies the self-consistency equation. This is something you can check essentially brute force by substituting into the equation, and you realize that that this is satisfied. Okay, and this is very, again, it must be viewed as a surprise because, again, let me restate this, that the fact that there is no natural separation of time scale in the problem. So usually the Markov approximation for a quantum buff is associated with the fact that the buff is very fast compared to the typical time scale of the system, and this allows you to approximate your reduced evolution of the system with some Limblad equation, right? So some effective Markovian equation. Now, in this case, there is no such separation time scale, and this occurrence of this Markovian dynamics is an exact statement, and this related to the fact that there is exactly no backflow of information from the environment to the system at those fine-tuned points. Of course, this is well, okay, let me first say this. So these fine-tuned points actually were known before to be sort of special, because these are points that have been discovered a few years ago by Aquila and others, and this is connected. I mean, the specialty of this problem of these points is that the system has an emergent space-time duality in a precise sense, and this has been exploited by Bertini et al. And collaborators to essentially to compute exactly some very non-trivial quantities such as the spectral correlations and the growth of entanglement entropy or spatial entanglement entropy. So okay, here essentially the particularity of these points shows up in the fact that the dynamics induced on local subsystem, it turns out to be exactly Markovian. And also another interesting observation here is that if you consider now the fully random version of your model, so you make the diagonal interaction between your spins fully random, so there is a fully random phase for each pair of states between neighboring spins, and you make your kick, your single spin kick, fully random also, so hard random, a random single spin unitary rotation, then the influence matrix of this fully random environment is also perfect dephaser. So this gives you some intuition on the fact that these special points sort of mimic the noise, the quantum noise produced by a fully random environment. Okay, so
can I ask you a question before you continue?
Please.
Or rather, no question, but can you quickly show again the model, the specific form of this kick model?
Yes, it's this. It's
okay. Thank you.
Okay, so it's just, well, the simplest version is just Ising type interactions. Okay, so diagonal interaction between neighboring spins and single spin kicks. Of course, here you want to avoid integrability, so you take single spin rotation that have both transverse and a longitudinal, so a generally tilted axis of rotation. If you tune your longitudinal component to be 0, this model is integrable in the conventional sense. Okay, so okay, this is exact Markovianity is I mean, mathematically you can phrase this as the statement that the influence matrix takes a product state form. Okay, so the action of the buff at time t is completely uncorrelated from the action of the buff at time t prime different from t. Okay, so it's linked, it's intrinsically linked with to the product state form of the influence function. So the full locality in time of the influence function. But yeah, so this in turn you can go back to the operator space and describe this as an exactly Markovian dynamics, as I said. In particular, in this case, due to the form of your interaction, this is a pure dephasing. This can be described as a pure dephasing quantum channel. Okay, and I already commented on this. And yeah, okay. Then, as I already said, this can be viewed as essentially as the buff produced in a classical white noise. So it's the most say chaotic action of a buff acting on your system. Okay, now of course this is not at all expected to be generic. Now these solvable points are special for many reasons, but this extreme locality of the influence functional in time is supposed to be a very fine-tuned problem. Sorry, a very fine-tuned point in parameter space. Now the interesting question here is what kind of, if there is any kind of robustness to this behavior. So of course what we expect is that when we detune our model parameters away from a perfect dephaser point, well, typically the buff will acquire, the system will acquire some range of temporal correlations. So our influence function will no longer be possible to express it as a product state, but it will be a short range correlated object. And therefore we expect that an efficient matrix product state representation of this object is possible. Okay, so this is what we investigate essentially. And okay, this is technically this amounts to solving the self-consistency equation by plugging an MPS ansatz essentially. So an MPS ansatz with a finite bond dimension, and then you want to maximize essentially to solve in the best possible way the self-consistency equation, and then you check consistency by increasing the bond dimension of your MPS. Okay, this is what we do. And in particular, you see that the slope of temporal entanglement of the self-consistent solution, when you detune your system away from a perfect dephasor point, the slope drops to 0 as you. So there is a notion of continuity in a sense, meaning that the temporal entanglement is parametrically low as you approach this fine-tuned exactly Markovian points. Okay, so here we want to use this as a computational tool to compute the properties of the influence matrix and link them to the physics of the system. Okay, so this is our primary goal. And okay, so let me describe how you can do that. Okay, so the first thing I want to share is essentially some intuition on what the influence matrix elements, so on how the influence matrix elements can be viewed. Okay, so now if you write down exactly the.
Could you go back a slide? Something. Yeah. So on these figures, the x-axis is time.
The x-axis is time. Yes. So it's the total. Say, okay. Sorry. Let me explain a bit better. So this is so we have this fictitious wave function in time from time 0 to time t, and this thing here that you plotted here is the maximal bipartite entanglement. So the maximal for all cuts in this wave function, plotted versus the total evolution time. So the size of the total time window. Okay.
Okay. So
and this is done for increasing bond dimension. Please.
I thought the claim was that this was going to have low entanglement, but this seems to be growing with, effectively with the system linearly.
Yeah, no, you're right. You're absolutely right. So this is low by tuning the parameters, not low by increasing time. Okay, so we actually don't know. I will comment.
Low is low parametrically.
Exactly. Yes. So the slope, if you look at the inset here, this is the sort of the rough slope of this initial growth versus the detuning away from the perfect dephasor point, and you see that this slope drops to 0 as you approach the perfect dephasor point. So in this sense, it's low. Now, it's very interesting to wonder what is the long time behavior of this quantity. I will come back to this later. Okay, so the type of scaling towards with respect to time. This is also very interesting, and I will come to that later. Okay. But okay, for now, I mean, so in this next few slides, what I will focus on is essentially to understanding the structure of this influence matrix, and essentially here I'm just using this MPS method just as a numerical tool to get the solution. Okay, I will come back to temporal entanglement scaling later. Okay, so as I was saying, one physically meaningful way to interpret the influence matrix elements is essentially to look at what it is, what they actually are. Okay, so if you write down exactly what the influence matrix is for a given trajectory of your probe spin, forward and backward in time, sigma and sigma bar, what you have to do essentially is you have to feed at the boundary of this environment, you have to feed some trajectory, so some configuration or in time-changing configuration of your spin according to the trajectory that you selected, and this acts as a field, as a time-dependent field on the first spin of the environment. So in this case, on spin p+1. Okay, so this influence matrix element can actually be, when you write it down, can actually be viewed as the overlap between forward and backward evolution of the environment subject to a boundary field that changes in time. Okay, now you immediately realize that if your forward and backward trajectories are equal, now the forward evolution is the same as the backward evolution, and so this trace just gives 1. Okay, so essentially this object probes the discrepancy between forward and backward evolution of your probe spin. Okay, so it's sensitive to this, and in particular you can view this as a sort of collection. So you can view the influence functional as a sort of collection of all possible time-dependent echo dynamics of your environment, subject to boundary perturbations, boundary field variations. Well, by echo, I mean the overlap between a forward and a backward in time evolution, which differ somehow. So in particular, this is, as I said, by this expression, you realize that the influence matrix is less than 1 generally, and it's equal to 1 when the forward and backward trajectories are the same, are equal. Okay, so let's investigate this. So this sort of trajectories, we call it paired trajectories or classical trajectories in the Keldysh path integral language. Okay, and the influence function has value 1 for them. Okay, and now if you go back to the perfect dephaser influence matrix, which is an exact solution for the when you tune your system parameters, this is nothing but telling you that the influence of a perfect dephasing buff is just to suppress all possible trajectories that are not classical, that are not fully paired. Okay, so this in turn means that your buff is fully suppressing local interference. Okay, it's essentially equivalent to white noise, as I already discussed. Now, what happens when you detune your model parameters away from this exactly solvable perfect dephaser points is that these other trajectories, these not fully paired trajectories, pop up and acquire. So they are strongly penalized, but not completely suppressed. So they acquire some finite weight. Okay, and so you can get some mileage here by calling the unpaired portions of your local trajectories as blips. This terminology is borrowed by this old work by Leggett and collaborators. And actually, you can view the influence function of a strongly chaotic but not maximally chaotic quantum many-body system as a sort of interacting blip gas. Okay, so there is a penalty in the influence function for the existence of a blips, and this is the way you can describe it. So we want to introduce some sort of statistical mechanics description for these objects. Okay, so the next few slides are just to describe what this interacting blip gas looks like. And the first thing to realize is that the price you pay for versus the size of the blip is exponential. Okay, so the suppression of your influence matrix elements is exponential in the duration of the blips. Okay, and this comes by just noticing that the influence matrix of an unpaired portion of trajectory is nothing but the Loschmidt-Echo. The Loschmidt-Echo, which is a signature of quantum chaos introduced many years ago, and it's sort of well known that this Loschmidt-Echo decays very fast in chaotic systems. Okay, so what you can do is you can compute this blip mass essentially, so the suppression of a single long blip as a function of its duration. And in this case, due to this remark, you realize that this decays exponentially in time. Okay, and this is also actually true for generic blips, so even time changing but still fully unpaired portion of a trajectory. Okay, so these blips are exponentially suppressed. This is the first message. Second message is we want to understand how they interact. Okay, so what is the extra penalty or absence of penalty you gain by putting some blips in your trajectory that are separated by some time separation. Okay, and now this I won't go into the details, but it turns out that you can rigorously relate blip interactions to temporal correlations, to correlations between local operators that are separated in time by the separation of the blips. Okay, so by virtue of this mapping, essentially you would expect that your influence matrix behaves as a good statistical mechanics form, meaning it behaves as a short-range interacting gas of particles. Okay, and this you can probe numerically by looking at individual configurations with blips separated by some distance, and you see that the influence matrix element for these configurations decays at long time separations to a constant value, which is just equal to the product, the disconnected part, essentially, to the product of the two influence matrix elements for the two blips, for the two individual blips. Okay, so essentially, if you take the log, this is just the statement that the faraway particles, so faraway blips, don't interact. Okay, so this is just a rephrasing of the fact that the interactions are short range. So in these plots, in particular, you see that these groups of curves are for increasing detuning away from perfect dephaser points. So of course, if you tune your parameter to perfect dephasing, the influence matrix is just 0. So the existence of blips is fully suppressed, as I already discussed. But as you detune away from them, they acquire some mass, some finite weight, but they are short range interacting. Okay. Now this picture of a weakly interacting blip gas is very nice. It's very appealing, but it's also practically useful because you can get advantage of it for making analytical predictions on thermalization. For example, for computing the relaxation rate of an impurity embedded in your chain. So consider, for example, spin P, which has some kicks that are slower compared to the rest of the chain. So essentially the strength of the kick acts here as a chemical potential for blips. So this is what allows you to essentially treat the blip gas as fully non-interacting, so as a fully factorized form of your influence functional. And this allows you to, with some calculation, it allows you to compute the no Markovian corrections to the fully Markovian results at a perfect dephaser point. So the decay of the polarization of this impurity in time, this is you have an exact result at the Markovian point, at the perfect dephaser point, plus some correction, and the dominant correction comes from non-interacting blip term. Okay, and then you can compare this analytical prediction to the fitted exponential decay of the polarization of the impurity, and you find that as you, of course, this is exact at the perfect dephaser point, but as you detune, the agreement is essentially perfect. And then, of course, at very large detuning, you acquire some discrepancy, and this discrepancy you can attribute to the blip interactions that you neglected. Okay, so essentially, this is how you can link essentially the physics of thermalization to the structure of the influence function. Now you can make progress on this by computing the exact influence functional for a solvable model, which is in our model. This is just obtained by tuning the longitudinal component of the single spin kicks to 0. So in this case, as I mentioned previously, your model becomes integrable in the conventional sense, meaning that it has underlying non-interacting fermionic excitations. So in this case, you can perform this computation exactly, and this confirms essentially the formula that you find for the influence function is Gaussian, of course, because the problem is quadratic. And what regulates the locality in time of the influence function is a function which is the fermionic analog of the spectral density of the Leggett problem, essentially. The spectral density, which is related to the spectrum of your quasi-particles. Okay, and in particular, what you find is that in the paramagnetic phase, so this model, this kick-teasing chain, this integrable kick-teasing chain has a paramagnetic and a ferromagnetic phase, depending if the interaction or the kick dominates against the other. Okay, and in the paramagnetic case, you find that this influence function is quasi-local in time, meaning this function that regulates the coupling strength between degrees of freedom separated in time decays with time. So this goes to the feature of being quasi-local. Instead, in the ferromagnetic phase, you have the appearance of long-range interactions. So for arbitrarily separated degrees of freedom in time, arbitrarily separated blips, essentially, you have persistent interaction, the persistent correlations. And this is related to the fact that this is the influence functional for a semi-infinite system. And in the ferromagnetic phase, you have the appearance of persistent boundary coherence in the problem due to the edge modes, essentially, these strong zero modes studied, for example, by Paul Fendley and others. And this local persistent coherence shows up in the influence functional as some long-range interaction between your blips. Okay, and in particular, in this solvable limit, you can prove generally for general parameters, you can prove that your influence function satisfies an area law scaling. So for example, that the tensor network approach to its computation is really favorable. And this happens throughout the phase diagram. In particular, you can compute the saturated value of your temporal entanglement throughout the phase diagram. So as a function of the interaction strength and of the kick strength, okay? And you see that the value of temporal entanglement bears a fingerprint of the phase diagram. Okay, so these diagonals that you see in this square on the right are actually the phase transition line, so the boundary, phase boundaries between ferromagnetic, paramagnetic, and the phases with Floquet edge modes. Because remember, this is the Floquet version of the problem. So you have also not only zero edge modes, but also pi edge modes, as discussed in many previous papers. Okay, so what is particular here is that the saturated value of the temporal entanglement shows jumps. So when you cross a phase transition, okay. So normally for ground states, for example, at a phase transition, you would have a logarithmic correction to the entanglement of the ground state. Here, this is an intrinsic non-equilibrium. An intrinsic non-equilibrium object here, so you shouldn't expect the same. And in particular, what you find is that there is a jump, a finite jump, and this jump is related to the existence of this edge mode. So to the existence of this extra quasi-particle mode localized at the boundary, which contributes finite amount of entanglement. And in particular, when you zoom close to these critical points, you realize that the saturation of temporal entanglement to its final area law value becomes critically slow. So if you rescale your curves by the detuning away from the critical points, they collapse onto some limiting curve. So this is a signature of a critical slowing down close to the phase transition. Okay, and finally, the remark I want to make is that you can take advantage of this favorable scaling of temporal entanglement to study integrability breaking. Okay, so if you now restore your longitudinal component of the kick, this completely destroys integrability, because this longitudinal field essentially is a horrible operator when expressed in terms of the quasi-particle of the problem. So it's a violent integrability breaking, and yeah. So what you can study is, well, essentially for weak integrability breaking, at least for weak integrability breaking, you expect your computation to be still very efficient, and this allows you to study the for example, dynamics of observables and temporal entanglement scaling under integrability breaking. And what you find is very interesting. So in the topologically trivial phase, so in the phase without edge coherence, you find that the temporal entanglement scaling is pretty insensitive to the integrability breaking. So in this case, in this plot number A here, so plot denoted A, which corresponds to a point deep inside the paramagnetic phase. Now you see that for the strongest integrability breaking that we have considered, which means taking a longitudinal field which is comparable to the value of interaction. Okay, so there is no sense in which this integrability breaking is small in this point. Essentially you see value of temporal entanglement very close to the area law value of the associated integrable point. Okay, so it's pretty insensitive. But this slowly changes as you go toward the other phase. So for example, in point B here, you see that it's still, there still seems to be an apparent saturation at long time, even for the strongest integrability breaking. Sorry, this dashed and solid are just two different bond dimensions. This is just to show convergence of the solution of the self-consistency equation. Okay, and you again see some apparent saturation, but as you enter the other phase, you see instead some very rapid growth. Well, some parametrically slow as you crank up the integrability breaking, but still rapidly increasing slope of temporal entanglement growth. okay, rising above the area law saturation, which you find for vanishing integrability breaking. Okay, well, of course, it's still unclear to us what this is, so we don't have a full understanding of this phenomenon. We think it might be related to the fact that, so we have seen that you have a finite jump in entanglement due to the existence of edge coherence. Now, as you consider a longitudinal field in the ferromagnetic phase, this leads, if you look at the spectrum, well, or the approximate spectrum of the problem, this is associated with the existence of a hierarchy of bound states, of kinks attached to the boundary of the chain. So, and if you think that bound states, so edge modes lead to more temporal entanglement, this might be the origin of this temporal entanglement growth. But still, I mean, this is just a suggestive idea, but some more work is necessary to investigate this. And finally, you can use this efficient computation of long-time integrability breaking dynamics to investigate, for example, local relaxation. And you see that concurrently, when the temporal entanglement entropy grows, you see a slower relaxation of local polarization. Okay, so this reinforces this idea. Okay, so how much time do I have, Achilles?
You have 5 minutes, or if you want, we can sort of bring it to an official close, and then. Yeah,
maybe it's better. So
if 5 minutes are not enough.
The last thing I wanted to mention briefly is this essentially how to extend these ideas to study many-body localization. But okay, if any of you is interested in this, I'm happy to briefly tell you how this works. But okay, otherwise, let me just say that the core idea is essentially the fact that you can exploit this method to take exact disorder averaging. Okay, so in this, it's very natural in this kind of approach to compute the average of the influence of an exactly disorder average path. Okay, and this is very natural because it still turns the problem into a self-consistency equation, which now the price you pay for exact disorder averaging is that your transfer matrix develops effective long-range interactions. Okay, but still, it's still possible to develop an MPS approach to deal with this problem, and this allows you to essentially eliminate disorder averaging once and for all from the problem. So it turns it into a translational invariant problem, and hopefully takes into account the effect of all, say, probability of resonances and things like that normally complicates a lot the analysis of many-body localized systems. Okay, and yeah, so this is the central idea, and yeah, we have started exploring many-body localization using essentially this idea. Okay, so maybe it's, as you suggest, it's better to stop here, and if anyone is interested in more details, I'm more than happy to discuss.
All right, thank you. So does anybody have any questions on what Alessio has already
tried this for these translational invariant MBL models like Stark MBL?
No, sorry. Let me rephrase it. So thing is, you make your model disordered. Okay, so let me just go quickly through it. So you make your kick-teasing chain. So let's stick to this model, which is quite common. And you make your longitudinal field fully disordered. So you substitute it with a longitudinal field that is fully random. So it varies from.
You're still doing this Ising, okay.
Yes, exactly. But then so here you see you break translational invariance, of course. So the influence functional on spin P is different from the influence functional on spin P+1 because the effective environment that each spin sees is different. But the crucial point here is that you can take your influence functional and perform exact disorder averaging. So this is actually hidden under the carpet even in the previous part of the talk, because in the previous part we always considered, for example, ensembles of initial states, for example, infinite temperature initial states. And this is also a form of averaging over an ensemble of environments. But here you can also average over an ensemble of Hamiltonian parameters, for example, over your disorder. Okay, and this turns the problem into a translational invariant problem. So it's still a bulk. There is still a bulk self-consistency equation which describes the action, well, the influence of a disorder averaged buff. Okay, of a disorder averaged system onto the local dynamics. So this is exactly the object that you need to compute disorder averaged observables. Okay, for example, here we compute. Sorry, it's not reported here, but you can compute the decay here. This one, you can compute the remanent magnetization. So essentially the local autocorrelation of the spin polarization, and this is precisely the probe that tells you if the system is deeply many-body localized, meaning there is a local integral of motion that overlaps with the bare sigma z operator. Okay, so this is a necessary and sufficient condition for strong many-body localization, essentially. Okay, and this guy is the exact disorder averaged version of this remanent magnetization is exactly the thing that you get out of the exactly disorder averaged influence function. Okay, so essentially the existence of this long time memory, so the absence of decay of this local polarization is encoded in the exactly disorder averaged influence function. Okay, in particular in the form of these long range correlations in time now. Is it clearer now? Or?
Yeah, I think I misunderstood because I didn't see the slides, but
yeah, sorry.
Yeah, so you the flow here. So what changes if you want to do Hamiltonian system time evolution?
Yeah, so okay, here you see that it's important. Having a naturally discrete time is important for the method because you end up with a spin chain in time, and so you want something discrete. But of course, the easy way to turn it, well, to go to the continuous time limit, for example, is viewing your circuit as a Trotter version of your continuous time dynamics. So for essentially scaling all your parameters by delta t. This naturally, well, this already immediately gives you the Trotterized version of your continuous time dynamics. And then of course the price you pay is that if you want to reach some finite physical time, then this means you have as many time steps as the inverse Trotter step that you took. So this turns into a finite size problem. System size problem, right? So the total time becomes the system size. But okay, up to that, this is definitely what you can do, and what we did actually in one of the papers that I mentioned to study continuous time dynamics.
So you're still quite limited in that case, but you have the benefit of doing the disorder averaging for free.
Well, not exactly for free. No, that's the point. Because this. So let me tell you. The price you pay is that you get this long range interaction. Well, it's very easy actually to understand, because this longitudinal field is a term in your Floquet dynamics of the form e to the I longitudinal field, disordered longitudinal field, times your sigma z. Okay, but now when you express it as a path integral, this is just e to the I your longitudinal field that couples to the total magnetization in time, to the average magnetization. Okay, and now if you take if you exactly average your path integral over this random field, what you get is essentially a term of the form of this form. So delta, essentially you are sort of imposing that the total magnetization of your trajectory on the forward part is equal to the total magnetization on the backward part. So you are projecting your spin chain, your fictitious temporal spin chain, on a sort of zero magnetization sector. And when you express this as an MPO, this is an MPO with large bond dimension, actually bond dimension scaling with the total number of time steps. So this is the price you pay for eliminating disorder. But it's still, I mean, we showed that it's still doable. So you can do that, and you can still solve variationally your self-consistency equation and get a good approximation of your influence matrix. Okay, that's what I meant when I said it's not really completely free, but at least you gain this self-consistency equation. So you gain this single equation instead of so you don't have to consider disorder fluctuations anymore, essentially. At least for the purpose of computing this remanent magnetization.
So what values is this disordered field taking? Do you have a finite set of values for this?
Sorry?
What kind of values?
Sorry. What I implicitly assumed that this here we took a fully random. So this disorder field H is a random variable uniformly distributed on the unit circle. So between 0 and 2 pi.
Mm-hmm.
Okay. Of course, if your disorder distribution is different, then you don't get an exact projection. You don't get a delta function as a result of the disorder averaging. You get something else. You get a function of the magnetization, which is not a delta function. And yeah, actually, we have some ideas on how to make further progress using some other, essentially not this method that I described in this slide, but some other MPS trick, essentially. Using a different distribution. But okay, say what I described here is the most naive and most direct way to do. Okay, so you just pick a longitudinal field which is fully random, fully uncorrelated in space, and just just a random phase, but constant in time, of course. And yeah, and this shows up after disorder averaging as a global constraint in your transfer matrix.
Are we assuming here that the disordered field takes values which are sort of uniform over the unit circle of the phase?
Mm-hmm.
Right. So this wouldn't work if you wanted to take like very weak disorder, and you can't like tune the strength of it.
Very weak disorder, yeah, you would get something else. You wouldn't get this delta function. But the point is, for any kind of disorder, you have to have long range interactions. That's the point, because disorder is constant in time. So the disorder field doesn't change in time. So it couples to all spin configuration at arbitrary times. And when you average over it, you couple all the spin configuration at all times. So it becomes an infinite range, intrinsically infinite range interaction in your action. And then this is local in space, but fully delocalized in time. And this is actually this is actually how MBL physics can arise, right? Because you have these long range interactions in time that hopefully, well, at least when they dominate, they lead to long range correlations in your path integral. So persistence of a spin magnetization in the time direction, right? It's the physics of the local integral motion. So this thing of having long range interactions is intrinsic to disorder. So whenever you have quenched disorder, you will get infinite range interactions. Then the specific form of this long range interaction depends on the disorder distribution.
You could just sample out of the disorder distribution and take some finite number of samples.
Maybe you have in mind some discrete disorder or something like that. So,
no, just sample from the distribution, even though you're not going to cover all the possibilities and it's not going to be exactly the distribution. If you did that, then each realization wouldn't have any entanglement introduced by a disorder average.
Wait.
And the hope is that you don't need to take a number of samples which scales with the number of steps, number of time steps.
No, sure. But then if you do that, you still have the problem of averaging at the end. No? I mean, you can consider individual samples, sure, but then, I mean, we thought at least that at least to us, one of the most appealing aspects of this was that you can forget, from that point, you can forget about a disordered model. No, it's just a translational invariant model, right? So this is what we aimed for.
You'll be getting more samples than you would appear to at first. Like this, you would be, as you iterate this process, going like adding additional spins, you'll be effectively covering all the different combinations of those random values that you could have got. Right? If you pick 100 different values on site P, in P plus 1, you've now covered 100 squared, correlated, albeit sort of patterns.
Right. But
so your method is still cheating a bit with the sort of realizations.
Yeah, no, I see what you mean. I'm not sure. Yeah, but so what do you have in mind? So
you can do this for like a distribution which is just distinct, like it returns just one number, and then you can just randomly choose a whole bunch of different samples, and then take the average of the application of that layer to the influence functional.
Yeah, right. So this is closer to the usual approach, right? I mean, you compute your what you want to compute using individual samples, and then you average at the end. Right?
Yeah.
Sure. No, this you can still do that. Sure. I mean, the price you pay is you have no longer a single self-consistency equation, so a single eigenvector equation. Now you have to pick up all the influence functions of all previous spins and just iterate your transfer matrix.
Or you can just add them all together. You don't really care like what the disorder pattern was on the left side. It's not going to influence the distribution that you're drawing the field value from the next side. They're all valid. It's the same reason why you're able to do this averaging inside the MPO. You can do the average outside of it. And if you do that, then you're not going to get something which has a dimension that scales the number of steps. And
yeah, I'm not sure I fully understood that, but sure. No, I mean, can be absolutely. Yeah.
Okay.
Are there any other questions? Or if Chris isn't finished, I'll just.
Yes. So we saw that we tended to get sort of like volume law entanglement away from special points with the number of time steps. So if we were trying to take this towards the continuous time case, where we have lots and lots of very, very small steps, would we see that the x-axis, should that be like the real time, or should that be the number of time steps?
So, say it again, which limit you want to consider?
So if I take a limit of towards like vanishingly small time steps, or
right,
up to the same amount of total time.
Yes. No, in that case, now let me just mention that. So you see, these perfect dephaser points are intrinsically Floquet, meaning the parameters of your gates are some order 1 numbers. Okay. So if you any time you want to go to a continuous time limit, you're doomed to lose this property. Okay. So you will end up very close from this. Very far from this poorly entangled point.
But if we were to be very far away from that, and we were to produce the same figure, maybe it would be difficult to go to very long times, but presumably the entanglement would grow with time. And
yeah,
not
actually
with a number of steps. At some point, you shouldn't really need any more entanglement. Like you shouldn't be able to like stick more correlations into temporal correlations into it under like finer and finer time resolutions. Like it doesn't have time to send the information and hide it somewhere.
Sure. I mean, you at some point you meet some redundancy essentially, because you're approaching something that has a finite time limit, and you're using many time steps just to produce some. Yeah, no, that I agree. And indeed, this if you try to do this for continuous time, you see this.
Okay.
You see this. So it doesn't blow up.
Right.
That's true. But still, I mean, what I wanted to mention is that this point, so if you look at this phase diagram here, this is the integrable phase diagram, meaning there should be a third axis here, which is the longitudinal field. And here it's tuned to 0. Okay. Now the self-dual point, this dual unitary point, is this point in the middle, this point where both critical lines meet. Okay, it's pi fourth, pi fourth. And this is extremely singular, meaning that so I mentioned that in this integrable manifold, you always have an error law. So at infinite time, you still have a finite temporal entanglement. And the saturated value of this temporal entanglement goes to a constant, goes to some 1 point something when you approach the self-dual point. So it's, I mean, this 0 temporal entanglement is very, I mean, this is why also this slow growth, actually this is what I wanted to mention before. So this slow growth that you see when you detune away from the perfect dephaser point is actually, it's likely more related to this critical slowing down, because the self-dual point is the meeting of two critical lines. So it shouldn't be, I think it shouldn't be meant as a volume law. It should be meant as the beginning of some initial raise that leads you somewhere, no? Because you would see this even in the integrable limit. And this is just a very slow growth, but it's just going to a constant. Okay. So yeah, this is why I mentioned you must have a note of caution where you look at the temporal entanglement scaling close to this perfect dephaser point.
So just one small thing. So are you saying on this figure you get a 0 at the points where they cross, and then and that's not the limit that you get if you approach it from within any of the phases or critical lines?
Exactly. Yeah. You see this red spot in the diagram. This is a 0, but as soon as you detune away from that and you go to very long time, this is not 0. It's just some constant, and this constant is actually independent of the angle at which you approach it. So it's a highly singular point in parameter space.
That's very strange.
Indeed, yeah. But you see, I mean, at least in this submanifold, you understand it perfectly because you have full analytic control on what is happening, and this is actually understandable, because what happens at this point is that your quasi-particle dispersion relation becomes exactly linear. So the frequency, the quasi-energy of the quasi-particle is equal to the quasi-momentum. Okay. And this is actually a result of this space-time duality, because space and time are the same, so quasi-momentum and quasi-frequency are also the same. And this linear dispersion relation essentially has a perfectly local in space in time Fourier transform. And this is why the influence functional in this limit ends up to be exactly local. Okay, but as soon as you detune away from this point, your quasi-particle dispersion relation bends. Okay, and so you will have saddle points, and your Fourier transform, which is the exponent that dominates the blip interactions in the influence functional, develops some algebraic tails. Okay, so this is why I say this is extremely singular.
You sound like very nice things. Really nice examples if you just want something to work.
Yeah. So because at the beginning, also what we thought of doing is setting up a perturbation theory around this point, but actually we realized it's a very singular point, so it's not easy.
Okay. Does anyone else have